Howdy, everybody. All right. Wait, we got 2 minutes. Sorry. 2 minutes? All right, we'll give them 2 minutes. Well, we'll split the difference. I'll do 26. Because we got 50 slides, a lot of demos. All right. And there's a greater than usual chance that everyone in the audience is not necessarily a native English speaker, and I have a tendency to speak far too fast anyway, so we'll do our best. All right. Actually, I think we'll get started. Howdy, everybody. All right. Today, I'm going to talk about application attack surface and some things that we've been doing to use calculating attack surface and more specifically watching attack surface change over time that helps us integrate application security testing into CI/CD pipelines. So I'll provide a little bit of background. I'll talk about the importance of attack surface, talk about how attack surface is relevant to the things that organizations are trying to do with DevOps, and then talk about this hybrid analysis mapping technology that we have developed and some of the history behind that. We've got some extra slides in the deck that show you how to install or have links to different things and show you how to do installs. I'll probably scoot over a lot of the install discussion stuff just because we are short on time, and that those are mainly in there for if folks want to replicate what I'm doing. And then we'll talk through a number of use cases that we have developed that we use or that we're using this technology and these techniques for. My background is I'm a software developer by background. Originally a lot of early server-side Java in the mid to late 90s, early 2000s. I did some early .NET work, but really what I've done for the last 10 or 15 years of my career is worked with organizations on how the software that they're developing impacts the security of their organizations. And so my background is as a software developer that has come into the world of security. And as distinct from other folks who may be out into the application security space coming from a network penetration testing background side. So I'm a developer who's focused on security. And that shapes the way that I approach some of these issues. And I help run the OWASP San Antonio chapter with a couple of other folks. Is everybody here familiar with OWASP Zap? Yes, that's good. We'll be doing some examples with OWASP Zap. Fantastic tool, and it's great it's great with its API and with its flexibility. It's a really valuable tool to integrate into different DevOps app security testing activities. Again, I've got some example code bases. We've got links to downloads, and so on and so forth. So if you want to, all these slides are online, so you'll be able to, if you want to play around with this stuff, you can do all that too, provided those links. So let's look at attack surface. And what do we mean by attack surface? When I talk about an application's attack surface, what I'm really saying is this is the set or the list of all the different ways that an attacker can reach out and touch your piece of software such that they can influence its behavior, because that's going to be the set of things that they can try to manipulate in order to gain some sort of advantage. When you think of a web application, really what we're talking about from a web application is anything in the HTTP request. So the URL, the parameters, the web method, headers, cookies, and things of that nature. In theory, your web application also has attack surface, and then it may be pulling environment variables in from the servers that it's on. But if that's where you're being attacked from, you don't really have an application security concern. You need an incident response vendor to help you, right? So when we think of an application attack surface from a web app standpoint, we're looking at all of the ways in the HTTP request that the attacker can influence the behavior of the application. If you extend that concept of attack surface to look at mobile applications, Internet of Things applications, these get more complicated because on a mobile device, you've got a mobile device that's pulling in feeds from the network. Maybe it's receiving input from the user, talking to web services and things of that nature. Same thing with Internet of Things. And so today we're going to be focused on attack surface as it relates to web applications, but I do think that extending that or continue to have questions about attack surface across additional types of applications is really valuable. And what we're going to look at using attack surface to do is to help us target in this case, dynamic testing. So we're going to look at how can we use the concept of attack surface to target automated dynamic application security testing, and how can we also use the concept of attack surface to understand or to target what we're doing in the manual assessment or manual penetration testing. So what does attack surface have to do with DevOps? If you want your talk to be accepted at OWASP these days, I think it has to have DevOps in the title. Jim Manico was making fun of me at a previous presentation. That may or may not be true, but what we've been able to do is to use this concept of attack surface to help us get really focused in what we're doing when we're doing some app security testing in a DevOps pipeline. And so let's look at what we want from security in a DevOps pipeline. And again, Etsy, Netflix are doing amazing things with security in DevOps. And there's links here to a blog post as well as a video from RSA this year. But when we look at testing, application security testing as part of a DevOps pipeline, we look at that in 3 phases. The first is the testing phase. We're going to do some sort of testing activities to determine, what can I learn about the security state of this software, for this given build that we've got right now. And one of the things that we found is a lot of application security testing tools and techniques don't lend themselves well to being put out of the box into a CI/CD pipeline because they run too long. When the organizations that we've worked with, anecdotally, what we've seen is, security typically gets a budget for a given run of the pipeline of about 8 to 12 minutes. That's kind of what we've seen are the bounds. If security is going to weigh in on the decision about whether or not to break the build, they get about 8 to 12 minutes to do that. And so you can't, for each given build, you can't say, cool, let's kick off like a 3-hour Fortify scan or a 4-hour app scan crawl of the application, right? You're not, as a security, you're not going to be allowed to introduce those synchronously into a pipeline. Certainly there is value in doing those testing activities, but those have to be handled in an asynchronous manner. You're not going to be able to wait to give a thumbs up or a thumbs down on a build based on those long-running testing activities. And so when you think of kicking off testing, app security testing as part of the pipeline, some of those tests, again, you may be able to wait for if you can get them within that window. Other tests, you may start those tests, but you're going to have to handle the results of that testing out of band later on. After you've done the testing, or at least the testing you're going to wait for, then you get to make a decision. So should this build be approved or not? Similar to if the unit tests run and they fail, we say this build is not acceptable. If the functional tests run but they fail, this build is not acceptable. From a security standpoint, how do you make a determination if a build is or is not acceptable? And in a perfect world, security would be able to weigh in and say, we're never going to allow critical or high vulnerabilities in a pipeline build. If we find any critical or high vulnerabilities, we're going to fail this build. Who would like to be able to do that? Great. Who thinks they're going to get to do that in their organization anytime soon? Because the challenge is, for most applications, they have legacy code that's in there, right? There's probably findings that already exist, and hopefully there's a remediation plan in place, but you're probably not going to get to break the build for 3 months waiting for all the cross-site scripting vulnerabilities to get sorted out, right? You don't have that kind of political power in the organization, for most of the folks that we work with. So another way to look at this is to say, potentially, let's say our policy is you can't introduce new critical or high vulnerabilities, right? That's politically much more tenable, because while we agree, like, hey, we don't like that these vulnerabilities are in here, but at least we've got a plan to fix them, they'll get fixed down the road. But everybody should be able to agree that we shouldn't be introducing new critical and high vulnerabilities, right? And so that's one of the things that we found is that security folks need to be flexible in a lot of cases and to understand this is what I'm going to be able to get from a security standpoint, and these are the things that are simply not reasonable for me to, for me to be able to expect. Finally, we need to take what we found and we need to report those out to the developers. And again, the best practice here is use the tools that the developers are already using. Standard. Put it in Jira so they're being tracked as bugs that need to be fixed. But also, we'll look at things like chat ops. How do we notify developers? Hey, this last check-in that you just pushed in, that has changed the security state of the application. You have new findings that are in there, or you've introduced new attack surface that you need to be concerned about. But again, the important thing here is you need to be putting these results into the tools that the development teams are already using. So, talk through a lot of this. Many security tools are running too long to be included in the pipeline build. So, full SAST, DAST. Security testing also includes manual testing, or comprehensive security testing is going to include manual testing, and that's going to be way too slow to include in most pipeline builds. But by looking at attack surface and as it changes over time, that can help us focus certain testing activities. So if we have a very limited time to test, we probably want to test the parts of the application that are the most likely to have newly introduced vulnerabilities, right? And that's going to be new parts of the attack surface or parts of the attack surface where the application behavior has changed. And so by understanding how attack surface changes over time, that lets us focus testing activities. And we can also use it to help us trigger testing activities to say, since the last time we did manual testing, this is how the application's attack surface has changed. With the limited amount of time that I had to do manual testing of the application, let me focus in on that. And furthermore, I want to redo a manual test, either on some sort of time-based basis or looking at the evolution of the application. Say, well, hey, every time we've added 10 or more URLs to the application, I want to have a pen tester come in and look at this stuff, right? Or every time the attack surface has grown or changed by 5 or 10%. So we've built, in conjunction with or funded by the U.S. Department of Homeland Security, a technology we call hybrid analysis mapping. And the original goal of this hybrid analysis mapping technology was to correlate the results of static testing with dynamic testing. So to take SAST results from a Veracode, a checkmarks, a Fortify, and to correlate that with dynamic results from a ZAP, a burp, an AppScan, a web inspect. And this was developed with the Department of Homeland Security's Small Business Innovation Research Program. And what we found as we developed this research is that we were able to do the thing we originally set out to do, which was good, but we also found other uses for the technology, and that's really what I'm going to focus on today. We'll skip over this just for time, but again, this was a really interesting use of this, the DHS, S&T, CSD, SBIR program. The government loves acronyms. And one important point to make is please don't assume that this talk is endorsed by DHS. This is me talking about the stuff that we've done, not them specifically approving our content. So that's potentially an important point to make. But our original goal, again, was to correlate between static and dynamic testing work. And after we made that work, we found out that we could make other stuff with that technology as well. So is everybody here familiar with dynamic application security testing, right? So you're going to typically spider the application to find the attack surface. You're going to start on the home page and you're going to act like Google. You're going to spider, find all the pages, the URLs, the forms that can be passed in, usually with some login authentication and session management stuff in there so that you can crawl and see the application beyond the login page. And then we're going to do some targeted fuzzing. We're going to send in SQL control characters. If we see a JDBC error message come back, we say, oh, that looks like there's a SQL injection vulnerability here. And a finding for in these cases looks like the CWE, or the vulnerability type. We use the MITRE common weakness enumeration, the relative URL, like where in the application or what page in the application are we on, and the entry point, which for certain vulnerabilities like a reflected cross-site scripting or a SQL injection are going to have a parameter or a cookie or something that where the payload was passed in. So we want to correlate those with static application security testing. So that's where we're going to use source code or a binary. We're going to do some analysis, build a model of this application. We're going to do data flow, control flow, semantic analysis. And again, this is just kind of a textbook SQL injection where we get tainted data in. It taints a couple strings along the way and then gets passed to a sensitive function. And really what we were trying to do was to find the relationship between the behavior of an application and the source code responsible for that behavior. So for each, what we essentially do is we need to first standardize vulnerability types. Again, we used MITRE for that. But we wanted to map, when I make a request to a particular URL, what code in this application is going to run to embody the behavior of that URL. And when I pass in a parameter to the application, where in the source code does that parameter usage show up? So from this, basically what we do is we look at the application source code, detect the language and framework, and build an attack surface model of the application. So we determine what are all of the URLs that the application will respond to, and where is the source code that's responsible to serve each of those requests. And we figure out what are all the parameters you can pass into the application, and where in the source code is that entry point into the source reflected. And from that, then, we can fairly easily coordinate static and dynamic results. So if I have a dynamic result saying reflected cross-site scripting for login.jsp for the username parameter, I can go query my endpoint database, and it says, well, this is a Java Spring application, com.whatever, login controller.java line 62 is the source code responsible for that. Then we look through our static findings and we find out, hey, there's a reflected cross-site scripting, and the source function for that is at logincontroller.java line 62, right? So that's how we're able to correlate between the static artifacts of the source code and the dynamic behavior of the running application. And so I was working with one of our engineers, and he explained how this worked. And I said, well, this is very impressive, but what else can we do with this? And so what we found is, like, with that data structure, we can do some interesting things. If you have a dynamic result, but you haven't done full static analysis, but if you have a dynamic result with for a vulnerability, you can query this and find out, like, well, where in the source code should I start looking for how I'm going to fix this vulnerability, right? That's not as good as most of the static analysis vendors have, like the plugins, and you can go through the full data flow and control flow. That's better, but if you haven't done that analysis, by having this data structure available, you can take a dynamic result and map it to an entry point in the source code. As we'll see, we can also do some interesting stuff where we can precede dynamic scanners. And so if we've got this application attack surface, remember, we're looking at the application source code and figuring out from that, again, where the behavior comes from each part of the attack surface. If you look at the dynamic testing, the first step there is to spider the application or to try and guess and discover the application attack surface. But if we can precede that scanner, we can hopefully avoid false negatives, right? So we can precede the scanner to say, here are all the URLs that you might that you want to test, and here are all the parameters you can pass in. Right, and so this helps you deal with like multi-step pages that you might not be able to crawl through and unused parameters. I worked on a Cold Fusion application once where if you passed in a parameter named D to any page in the application, whatever value that was, let's say you pass in a parameter of D with a value of 1,000, it would delete order number 1,000. Why? Nobody knows. So by calculating this attack surface, you can know about that beforehand. So we've taken this technology and embedded it in a number of different things. And so we've got a command line client that you can use, point to the source code, and dumps it out. That's handy from a standpoint of it lets you do a visual quick check to see how big is this application, what are the parameters, and you can look in to see if you find any parameters that have scary, weird names like debug, right? And what it also does is it will go in and show you for frameworks that use auto binding, like Spring and Ruby on Rails, it'll parse the model files and show you situations where, hey, I can actually auto bind like 6 levels down in the in this parameter, and that's probably not the configuration that you want. We also have plugins for OWASP, ZAP, and for Burp that let you precede scans. So if we go and look at the budget store here, and we go and say I want to import endpoints from source, that's where my source code is. We can precede the scan, and what we see is that you are going to see things. Since we did that unauthenticated, we're going to find things like this admin.jsp page that you wouldn't find in an unauthenticated crawl, and you're going to see things like these debug parameters that you would also never see in the HTML or JavaScript that the application is rendering. All right, and so we're going to potentially find parts of the application that were not there before. So let's now think about looking at this over time. And so that's looking at the attack surface at a stationary point in time. But what if we say, let's look between 2 Git commits so we can see how the application has changed. And so, for example, here, what this lets us do is it lets us look between 2 different Git commits. And so we see between these Git commits, We added the attack surface of these 4 URLs. We didn't delete any attack surface, and we've got some percentage calculations there, right? And so we can start to see, hey, if the last time I did a manual test was here, and now I'm here, this tells you, you may want to focus your efforts on these particular URLs because they are the ones where it's most likely that we're going to find some sort of new bad behavior. We can also, by looking at the files that were affected by these, by the git commits in between these two points in time, by looking at all the files that have changed and correlating those to the files associated with attack surface, we can also calculate URLs where the behavior of those URLs may have changed. Like, this isn't perfect because we're not actually doing a full analysis through the AST and a full data flow or control flow. But what we're doing is saying these files have changed and these files are associated with attack surface. So here we can see we've got the added attack surface, we've got the deleted attack surface, but we also, by looking at the files impacted by the commit, see the attack surface whose behavior might have changed based on the changes that were made. And so that, again, gives us additional information about how this application's behavior may have changed over time. And so I can use that to focus our testing activities. So one moment. So now, and that is not what I wanted to do. So what we can do is we can watch a Git repository. And there we go. We can watch a Git repository and watch for changes. And typically this would be something you do with your CI/CD server like your Jenkins or your Bamboo. In this case, we're going to do it just by polling because it's easier to set up. But if we go in here and if we create some new attack surface, search. Yep. Now, if we push this out, what we see is over here, it's going to pick this up, it's going to detect this new attack surface, and then it's going to do a very targeted scan only of the new attack surface that has been added to the application. So we're doing a dynamic test with Zap, not crawling the entire application and fuzzing all of the pages, but instead we're doing scanning very specifically of only the pages that were added between those two commits. And so, using that technique, we can get much more focused in the way that we're doing our Zap testing, and we can use that then to post out to things like HipChat or Slack to let folks know, hey, for this commit that just went in, I did tests of the pages that are new and the pages that have changed, and we've detected this new XYZ vulnerability in there. The goal here being, and again, this is not a replacement for a full application security program where you're doing static testing, dynamic testing of the entire application. But the goal here is, by limiting the test time or the length of the test runs, we can get this very focused on only testing the new stuff, with the hope being that we can identify vulnerabilities much earlier in the process and let the developers know about them in the tools that they're already using, so that you don't have to go through this giant cycle where you find something, report it, it works its way back through the system. Instead, the developer can see, oh, for this thing I just checked in, there's 2 reflected cross-site scripting vulnerabilities. I need to go and fix those right now while I'm in the code, while I'm used to it. So again, I've got links to a GitHub repository. One thing I'll warn you, and this is from an actual call we had with a customer, where the customer actually said, Dan, so this functionality is available in that crappy kind of code that you write? And I said, yes, it is, because that's the way that we develop things. Is I Python things together and then dump it on our engineering team, and they make actual working good code out of it. So this stuff right now is still in the not quite Pythonic stage. But again, all these artifacts are out there in GitHub if you want to take a look and replicate some of this stuff. And we've got some basic libraries in there that will do the attack surface diffs, that will, and then have some Git utility functions that you can use to, again, kind of wire this stuff together so that you can see these examples. Any questions? I think I have 2 minutes. Any questions? Yes?
How do you identify the attack surface? Just looking for the files or?
Yeah, so the question is, how do I identify the attack surface? How do we identify it? So when you point the engine at some source code, it detects the language in the framework, and so it'll say this is a Java application using Spring, or this is a ASP.NET application in C# or a web forms, or Ruby on Rails application. And so we're limited right now in the set of languages and frameworks that we support, but it detects that language and framework and then goes through the source code and identifies, like for Spring, for example, it's going to go and it's going to identify all of the controller classes that have that annotation. It's going to parse out what URL is this attached to. It parses the model so that it can make those trees, parses the auto binding configuration, and so then it could say like, hey, because we understand how Spring translates URLs, we can do the same thing with like struts or web forms and things of that nature. So that lets us go in and calculate that attack surface that then gets fed down the line to other stuff. Yes. So the question is, does it work with the web services REST API? It does, I know, for Spring, and I'm pretty sure for Ruby on Rails. And so yes, I know I specifically worked more with the Spring stuff, but yes, it identifies those annotations indicating that those are web service methods and exposes those. And so like a really handy thing that you can do with this if you're doing mobile application pen testing with a Spring REST-based backend is you can use this to enumerate all of that attack surface, and you don't have to go through the full process of taking a mobile app, chaining it through Zap or Burp, and then watching all the traffic. So here are all the endpoints that we need to talk to. So
if you want to talk to Dan some more, he'll be out in the hallway afterwards.
all right.